Hello ladies and gentlemen, welcome to the module 2 of this reservoir simulation course. This module is called Tutorial in General Structure and Input Data File, and it will be divided into different videos. During the first video, I will show you the general structure of a data file. Afterwards, I will explain the main forces acting in the reservoir, and finally, I will show you some examples of how one of these forces can act in the reservoir. Once the contents and objectives are clear, let's start with the general structure of a data file. The structure I bring you today is specific for Eclipse simulation software from Schlumberger, but it is very similar in any other simulation software. In an Eclipse data file, there are 8 different sections. Let's review them one by one. The first section is run spec. It means run specifications. In this section, the title, the model dimensions, the phases or components present in the model are defined. Grid is the second section, where the grid geometry, the rock properties such as porosity, permeability, net to gross are specified for every single defined cell in the model. The third section is edit. This section is not mandatory. It means that the model does not need the section in order to be run. This section is used to make property modifications in the original grid. The next section is prosp. That means properties. In this section, all the information related to the interaction between the rock and the fluid is input. The main information to be input is the fluid model, the relative permeability curves, and the capillary pressure curves. Regions is the next section. If the computational grid needs to be split because there are different regions with different fluid properties, region section will allow you to specify which fluid model or relative permeability curve apply to each of the regions. The next section is solution. In this section, all the initial conditions are set. Information about the initial pressure at center datum, initial fluid contacts such as water oil contact, gas oil contact, capillary pressure at fluid contacts, or fluid density, among others. Summary is the section, and like edit section, is not mandatory to be defined as an Eclipse data file. Here is where you specify the output data and vector you are interested about your model. As you can imagine, it is not mandatory in order to run the model, but if you don't specify any output, you will not be able to understand and analyze your model. The last section is schedule. This is the only section where the order of the keywords is important. The information to be input in this section is very related to the operations to be simulated in the specific point of time, to put new wells or change rate. Now that we have a clear idea of the structure of an input data file, let's see the main forces acting in the reservoir. Always when the fluid occurs through a porous media, its displacement is affected by 3 different forces. The first force is the gravity force. It is always present in nature, and it works exactly the same in the reservoir as at surface. Gravity applies to anything with mass, and the vector of this force is always vertical and downway. Capillary force is the second acting force. This force is the result of the interfacial forces acting among oil, water, gas, and solid in a capillary or in a pore throat. This force will determine the pressure difference across the interface of 2 different fluids and the capillary or a pore throat. As an example, you can observe that if you put a straw in a glass of water, the fluid level in the straw will be higher than in the glass. The last acting force is the viscous force, and it is defined as the product of molecular friction between individual particles. This force does not exist in static conditions and only appears when the fluid starts to move. The direction of this force is always parallel to the movement of the fluid, and the most important factor of this force is the viscosity factor mu. Once we all know the main forces acting in the reservoir, let's see some examples on how these forces act. First of all, let me introduce a case study from the Institute of Petroleum Engineering at Heriot-Watt University. In this case, as you can see, in the first table, we have a grid of 50 cells in X, 1 in Y, and 15 in Z. It means a total number of 750 cells. The model is divided in 3 different layers, and as it is set in the property table, the layer number 1 has better properties in terms of porosity, permeability, and net to gross. In the last table, the main fluid properties in the existing phases, oil and water, are described. There will be 1 injector in one corner and 1 producer in the opposite corner. In the upper plots, there is a graphical interpretation of the relative permeability curves and the capillary pressure curve applied to layer number 1. On the other hand, in the lower plots, there is a the same plots, but applied to the layer number 2 and number 3. As you can see, analyzing the relative permeability curves, the residual oil saturation is in layer number 1 is 15%, and in layer number 2 and number 3 is like 25%. The reusable water saturation is 20% in both cases, so it means that there is a more movable oil in the layer number 1 than in the layer number 2 and 3. Comparing the capillary pressures, it is very easy to notice that the capillary pressure in layer number 1 is like half of the capillary pressure in the layer number 2 and 3. Having described the model configuration, let's see the first example about gravity forces. In this example, we will study the gravity forces acting in the 3 different models. The first one will be configuring as described in the previous slides. It means that the maximum permeability is at the top of the layer, and from now we will refer to this case as the base case. The second model will assume that the maximum permeability layer is in the middle of the model. And finally, the third model, we will assume that the maximum permeability layer will be at the bottom. In order to make these modifications in an Eclipse data file, modifications in grids and regions sections will be required. As you can see in the saturation profile, after 3 years, the water advances more quickly through the maximum permeability layer in all the cases. After 5 years of simulation, it is possible to observe that the water injected is still sweeping oil to the producer, but there is still a lot of unswept oil in all the cases, especially in the bottom one. Finally, after 10 years of simulation, it is possible to see that the top model almost swept all the oil. This is due to the injected water advancing the maximum permeability layer, as in all the cases, but with the difference that this water, due to the positive action of gravity forces and vertical communication, also swept oil in the vertical direction. In the bottom model, exactly the opposite happened. The water advanced in the maximum permeability layer at the bottom, and due to the negative action of gravity forces, all the water traveled through layer, leaving a lot of unswept oil in the top. Let's analyze this behavior. Analyzing these results with these 2 plots, we can see that in the first plot, we have the field oil efficiency or recovery factor, and in the second plot, we have the field water cut. The higher recovery belongs to the green case, where the maximum permeability was at the top of the model. This case had the help of the gravity forces in order to improve the sweep efficiency in the entire model, and for that reason, the water breakthrough was delayed compared with the other cases. On the other hand, as it was previously said, the red case, where the maximum permeability was at the bottom, the gravity force led to have a faster water breakthrough and lower recovery factor due to all the water went through the bottom, leaving a lot of unswept oil at the top. In the following example, we will study another cases of gravity forces action. This time, we will compare our base case model, where the vertical and horizontal permeability ratio is about 0.1, with another model where this ratio is 1. It means that vertical permeability is 10 times greater than in the base case. We also study a third model, like the base case, but with zero transmissibility. It means impermeable between layers. The fluid cannot flow vertically through layers. In order to make all these modifications in an Eclipse data files, only modifications in grid sections are needed. As you can see in the saturation profile after 3 years, in the case where the permeability ratio is 1, the fluid displacement is very stable and efficient. In the case impermeable between layers, it is observed that the water flows through each of the layers, but without interacting to each other. After 5 years of simulation, it is possible to see that the case with permeability ratio of 1 has swept almost all the oil without unswept areas. On the other hand, the case impermeable between layers, it still has a large amount of oil to be recovered. Finally, after 10 years, it is evident that the case with permeability ratio 1 has produced almost all the movable oil. On the other hand, the case impermeable between layers still has a lot of oil to be recovered. Let's analyze these results. This time, in the recovery factor plot, we can see that the yellow case corresponding to the permeability ratio 1 case is the highest. The main reason of that is due to the good vertical communication. The gravity forces made the waterfront advance like a perfect piston. This kind of displacement is very efficient and leaves very small quantities of unswept oil behind the front. On the other hand, in the red case, with no communication between layers, all the layers are swept independently, without any gravity assistance, and for that reason, the recovery factor is lower. Observing the water cut plot, in the case with perfect piston displacement, the water breakthrough is delayed in time and increased from 0 to 100 in just a few days. With this example, we arrived to the end of the first part of the Module 2. I hope you enjoy it, and I'm looking forward to see you soon during the second part. Bye.